Is it visible, the entire screen? So may I start? Okay. So first of all, good evening to all of you, and also happy new year to all. So I assume that your beginning of this new year is all okay. And and before going to the lecture, so let me just introduce myself. So myself, Samaresh Ghosh, and I am a PhD scholar in Department of Polymer and Process Engineering, IIT Roorkee. So for the PMRF, I have to do my TA shift. So that's why I have enrolled in NPTEL as a TA. So here we will discuss. I will not teach all of you. I will discuss with you, and also I will learn from you all. So I don't know whether you are all in academics or maybe somebody are in industry. So we'll discuss the course name of this session, and that is Characterization of Polymers, Elastomers and Composites, already taught by Professor Santanu Chattopadhyay. So he is also my teacher when I was in IIT Roorkee in rubber technology department. So before coming in PhD, I did my MTech from rubber technology, and now I'm here in IIT Roorkee. So okay, I will start now. So this is the first week doubt clearing class. So we'll discuss some question. I will summarize few basic concept, and if you have doubts at any time, you may just unmute yourself and ask me question. So here first we will go through one by one. First, the definition of polymer. What is polymer actually? Then classification of polymer. What are the different classification? There are many types of polymer based on different classification technique or methods, and finally different application. And then we will learn the structure property relationship. So that is very much important. If you know the chemical structure, you can guess some properties. It may be chemical, it may be physical, and based on that, finally you can process your material, and ultimately you will end as a end product. So before processing, before synthesizing, you have a little bit knowledge that the structure, how I can tune the property by tuning the structure. Okay. So from the name itself, that is polymer, basically that is a combination of different monomer or mar. Mar mean parts. And you know that carbon has the catenation property. So that's why mainly polymers are based on carbonaceous material. And we know that carbon can form maximum 4 bonds, and also the catenation property means it can bond with itself, that is carbon to carbon bond. In that way, it can bond with different molecule and form a large bulky molecule. 1 minute, someone is waiting. Let me just admit them. So, so this is the repeating unit. You may say this is CH2 and CH2. That is the carbon, and there is two small atom, that is hydrogen, and these two are the end group. It may be same type of functional group, like if you are starting with CH2 double bond CH2, maybe that is CH3, or maybe some chain terminus being agent. Based on that, the end group will be different. The main backbone is the CH2 CH2 CH2. So that CH2 CH2 is the repeating unit in case of polyethylene. It may be different for other type of polymer. Say if it is polypropylene, so it will be CH2 CH CH3. Then we will go what are the different classification of polymer. So you can classify polymer in various type of polymer. Say if I start from the origin of based on origin, so from here it is synthesized or it is developed. Based on that we can differentiate in three category. One is the natural, the next one is the synthetic. So synthetic means you are synthesizing in laboratory or in any industry, and the third one is the semi-synthetic. So this is the combination of two different polymer based on origin, that is some part is from naturally synthesized or naturally made, and another part is completely synthesized in lab or in industry. So example of natural, if somebody responds, so it will be enjoyable for me also, otherwise it will be boring. So if you give some example of natural polymer, anybody please, one or two example of natural polymer. Rubber is a different category. So you see there is another classification, that is elastomer or rubber. So it's a broad part of a polymer. But if you say rubber, it will be natural rubber. So only natural rubber, that is 100% naturally prepared or naturally synthesized polymer. And aloe vera, yes, that is also a naturally synthesized polymer, and it's a viscous type of material. It may be some protein or cellulosic components are there. So natural rubber is a purely natural polymer. Cellulose, that is also purely natural polymer. And except rubber and cellulose, there are some proteins. There are cotton. Cotton is also, that is basically cellulose. So that is also naturally synthesized polymer. And the synthetic polymer, those we are already from early morning before going to bed, we are using the synthetic polymers like your brass, your table, chair, and many things. So example is uh, polypropylene, polyethylene, polystyrene, all are synthetic polymer. And if you give some example of semi-synthetic, please someone, semi-synthetic example polymer, those some parts are from naturally synthesized and you incorporate something that is already it's not naturally available. PVC is purely synthetic. It's not naturally occurring polymer because there is vinyl group and chlorine. So monomer is the vinyl chloride, and you are preparing polyvinyl chloride. But vinyl chloride, the monomer itself, is not available in nature. You have to prepare vinyl chloride first and then PVC. PLA, uh, PLA. If you say the full form, it may be polylactic acid, or what you I mean you what you mean polylactic acid. Yeah, that is semi-synthetic. Yes, and better if you say that NBR, that is natural nitrile butadiene rubber. Sorry, natural rubber with brominated rubber. If you are compositing that natural rubber and butadiene rubber, or it may be EPR, epoxidized, sorry, ENR, epoxidized natural rubber. So that natural rubber part is already available in nature, and you are epoxidizing the that uh, monomer unit, that is isoprene, and you are synthesizing the uh, epoxidized natural rubber. So that is semi-synthetic type of polymer. So these three are the based on origin. We can classify polymer in three different class. The next one is based on thermal response. So first one is the thermoplastic, second one is the thermoset, and third one TP is, that is basically thermoplastic elastomer. So thermoplastic means you can process it as a plastic material. So by providing heat or some mechanical stimuli, you can process it. The thermoset, that is basically cross-linked. If it is cross-linked, you further cannot process it. That is thermoset. For example, cross-linked rubber, any cross-linked rubber, that is thermoset. For example, your phenolic resin, that is thermoset. You cannot, after cross-linking, you cannot process it. But the advantage of TP, so that is the combination of both. You can process it as a plastic, but it has some behavior like elastomer. So that's why TP is right now very much important in today's world. There are so many applications. For some soft touch application also TP is very much applicable, and there are other lots of application also. So based on thermal response means if you provide heat, whether it is uh, flowing or not, based on that you can categorize in three different class. That is thermoplastic, that is processable, that is thermoset. The next one is the thermoset. It cannot be processable if it is cross-linked. And the next one is the TPE, that is behavior like elastomer, but you can process it as a plastic. The third one, that is the most important one, the main three category of polymer is elastomer, plastic and fiber. So what is the difference of elastomer, plastic and fiber? If anybody responds, how you can differentiate a material, a polymeric material, whether it is a elastomer or rubber, or it is plastic or fiber? Please, how you can differentiate any polymer? That, okay, if this material, this polymer has these properties, I can say it is a elastomer or plastic or fiber. Uh, One by one, please. Plastic material obviously rigid, but if I say that if you cross-linked elastomer, you may sometimes get rigidity like plastic. Even if you can say fiber is more stiff than plastic, is not it? If you are saying nylon is very much rigid and it has much higher tensile strength than your plastic. But how you can differentiate it? So I can suggest that if I say, I mean, you can go in deep. I mean, from molecular level, you can say, from molecular level, try to understand from molecular level how you can categorize the polymer in these three categories. Yes, yes, somebody was responding. Yes, yes, that's very good. Yeah, that's a good reason. Okay, so from molecular level, the most important parameter to be a elastomer is it has to be very high molecular weight in the range of 10 to the power 5 or 10 to the power 6. If you compare it with plastic or fiber, you see that the molecular weight not that much high like elastomer. If you say natural rubber, it has molecular weight in the range of 10 to the power 6 order. But plastic or fiber, those are not in that range. The second thing is elastomer is mostly amorphous compared to your plastic and fiber. And the another important parameter is the glass transition temperature. To be a elastomer, the polymer must have a Tg well below room temperature. Until and unless it has that much of low Tg, you cannot say it's a elastomer. For any example, it's NR, SBR, BR, whatever thing, all have the glass transition temperature well below the room temperature. It may not be minus 10 or minus 5, more than minus 50, minus 80. And the crystallinity, the most crystalline is the fiber, then plastic and elastomer. Because you know that Tg, we will discuss in later slides, the Tg depends on what are the properties that can control Tg, Tm, etc. So these are the most prime three factor. One is the molecular weight, the second is the crystallinity, third is the glass transition temperature. Based on that, we can categorize the polymer in three class: elastomer, plastic, and fiber. And obviously, their physical property like mechanical property or uh, other solubility, these are also different based on their molecular structure. And from the chain structure, you can categorize polymer in two different. These are mainly for the synthetic one, that is homopolymer or copolymer. If it is polyethylene, that is homopolymer. If it is a in the backbone chain, it has different repeating unit, then you can say it is a copolymer. For example, EPR, ethylene propylene rubber, that is a copolymer. So based on the backbone structure, we can categorize in two different class, that is homopolymer and copolymer. So homopolymer must have a same repeating unit throughout the chain. In case of copolymer, it has to have a two different repeating unit. You have understand this, that copolymer, it's not like if you say the chain the repeating unit is CH2 and then CH2 then CH2 CH3. If it is repeating same, then it is not copolymer. Copolymer is two different repeating unit, it is not same repeating unit. Okay. Based on crystallinity, this is a you can not say it's a wide variety of polymer, class of polymer. Just in plastic, you may have some semi-crystalline nature, you may have some plastic, those are mainly amorphous. In case of elastomer also, some are semi-crystalline, and maybe you can induce crystallinity. For example, in case of NR, you know that that is responsible for a strain induced crystallization. And amorphousness, obviously polymer are mostly amorphous, but few polymers have some crystallinity in their structure. And also the based on the chain structure, that may be linear. For example, polyethylene, it may be branched if it is a copolymer, or like graft copolymer, or branched some bulky molecule to induce different property, you can induce branches. So based on the structure of your repeating unit, it may be linear, branch, and also branching, there are different polymer, you know that. So these are the broad category of polymer, how we can categorize polymer. The next one is the very important thing is the structure property relationship. So mainly three property, that is crystallinity, molecular weight, and flexibility. These three property in a polymer structure ultimately decide what will be the property, final property of your material. So crystallinity, flexibility, and molecular weight, these are also depends on the main monomer structure. What are those parameters? Like if somebody has monomer like only CH2 and CH2, and another polymers, for example polystyrene, that is CH2CH and one benzene ring, their property is different, their flexibility is different, and molecular weight obviously is different. The structure means the structure of your repeating unit or monomer. Then there are, whether there are some heteronuclear molecule, for example acrylonitrile, CH2 CHCN, there is one polar group, there is nitrogen, and bonding, different bonding and interaction. So these four parameters basically determine the crystallinity, flexibility, and molecular weight. And based on these three, the physical, chemical, and mechanical properties will be different. So if I ask you that if I induce a aromatic chain in your backbone, what are the properties will be improved and what are the properties will be uh, inferior compared to your pristine one? Anybody please? If I induce some aromatic ring in your backbone, what will be the changes? What will be the different changes happened in your final material property? Anybody please? So first, just think what will be the effect on crystallinity, flexibility, and molecular weight. Say polyethylene, that is CH2, and in case of polystyrene, that is CH2CH and one benzene ring. What will be the changes in crystallinity and flexibility? Anybody please? Molecular weight will increase. I'll discuss the molecular weight concept also. So if I say one has the repeating unit of 1000 and another polymer, that is CH2C6H5, that has uh, that is extent, degree of extent, that is 200. So obviously you cannot say it will ultimately impact in molecular weight, because molecular weight, we know for case of polymer there are number average, weight average, and that depends on the extent of reaction. Understand? In case of polyethylene, if the extent of reaction is 2000 or 5000, and in case of polystyrene the extent of reaction is, or degree of polymerization is 200 or 300, you cannot say ultimately the it will hamper your molecular weight. Yes or not? Let's assume that both have the same degree of polymerization, then how it will change the polyethylene polystyrene? Yes, chemical property will be different. Exactly, because of that aromatic ring, it has some uh, electronegativity because of sp2 hybridized carbon, and also it is bulkier compared to your hydrogen. So the main changes will happen in the crystallinity and flexibility if I assume that both have the same degree of polymerization. If different degree of polymerization, then I cannot compare in molecular weight, because some chain will have 200 repeating unit or 2000 repeating unit. So I cannot say that, I cannot comment on that. But the obviously crystallinity and flexibility will change. Why flexibility will change? Now I am substituting the hydrogen atom with a benzene ring. So it will be difficult for the segmental motion of your chain. Yes or not? In case of ethylene, it is only hydrogen atom. But in case of polystyrene, now I am substituting that hydrogen with a benzene ring. So it will be difficult uh, to mobile at a particular temperature for that in case of polystyrene. So flexibility will reduced and crystallinity also will be reduced. So here I will ask one question. So I have already told you that elastomers should have a Tg well below room temperature. Now my question is, if somebody know, please give me answer. What is the Tg of polyethylene? Anybody please? What is the Tg of polyethylene? No, it's not 65. Somebody else? More than? No, it's not. It's not in positive. It's not in positive range. It's not in positive range. It's in minus. Yeah, yeah. And, it's not minus 125. It is around minus 115 to minus 120. The least Tg, that is silicon rubber, that is minus 125 degree centigrade. Now my question is, now it is well below your room temperature Tg. Your natural rubber has Tg around -73, but in case of polyethylene it is -115 or 120. Still it is plastic. What is the reason behind that? You got my question? Higher molecular weight, if you say higher molecular weight, it's not in the range of natural rubber or other rubber, but still it is plastic. Just think it, why it is plastic, even it has a very low Tg. So I'll just go. Yes, that is the main reason. It has a crystallinity. It has a around 65 to 70% crystallinity in the structure. Now why it has that crystallinity? The reason is because of its very simple structure, that is CH2 and CH2. That's only hydrogen atom is attached. Two very small hydrogen atom is attached with one carbon. Because of this, that very simple linear structure, the number of chains can stack with each other. Because of that efficient stacking, it has a good crystallinity. And as we know, higher the crystallinity, higher will be the mechanical property, and it will ultimately towards plastic. Because of that, even it has a very low Tg. The only exception, polyethylene, is plastic. Understand? And that's why it has also flexible also. So now you can answer that why the monomer structure ultimately determine what will be the properties and also its physical appearance. Now if we say about what is the role of heteronuclear molecule, say nitrile rubber, NBR, acrylonitrile and butadiene, that is also example of one copolymer, and it is in elastomer category. So it has CH2 double bond CHCN, one monomer, and another monomer is butadiene. Now you maybe know that it is mainly applicable for automotive purpose and also other oil resistant property, oil resistance application. So if I have to use some polymer or polymeric material in oil resistance application, so I can think that what will be the my monomer molecule structure or atomic structure. Based on that, I can assume that it should have this property. Now we know that mainly oils are very non-polar nature. Those are very uh, organic moiety, and there are no as such a polar group. So we have to use some polymeric material that has least interaction with your oily material. Now in case of CH2 double NBR rubber, because of the presence of CN group, and it will create the polarity in your molecule polymer. Because of that, it will ultimately resist your oil. So based on that, we can also assume what will be the final properties, and based on that we can determine that where I have to I can use my material. And this bonding and interaction, these are depends on the structure, these above three parameter, that if there are polar groups, so obviously there must be some polar interaction, there may be some hydrogen bonding. So these four parameters ultimately decide these three things, and these three things ultimately you decide your thermal properties. So if I say that if some polymer has a degree of polymerization around 1000, and the same polymer which has degree of polymerization around 500, so there will be change in the molecular rate. Understand or not? If some same polymer has degree of polymerization 1000 and the same polymer has degree of polymerization 500, the molecular weight will be different, because in case of polymer it is not a single molecular weight. That's why we need to calculate the average molecular weight. because it's not a single molecule. There are branches of molecule. So if molecular weight is higher, what will be the mechanical properties? Anybody please? To get higher mechanical properties, what will be the my pre-assumed property that material should have, so that I can apply it in a higher uh, high end application, like in case of tire. So it is in a high end application, it has to have a very high mechanical property. So what elastomer you will choose? Anyone response please? Yes, it. Yes, yes, yeah, that is true, that is true. Yes, higher molecular rate, because higher molecular rate ultimately has higher mechanical strength, and there are different mechanical properties also, so we'll discuss in later. And also the thermal properties you have already told, that higher the chain length the flexibility will be higher, and also your thermal properties will be uh, based on different application we can use in different part. The next is the chemical properties. Say if I want some application in outdoor application for any elastomer, so how I can design that, what are the prime properties the elastomer should have, so that I can apply it in outdoor application? Anybody please? That is true, that is true, UV range. Okay, so now my next question is, that is true. Now my next question is that for UV resistance, then what, how you will decide the molecular structure? I mean, what should be in the backbone structure, so that it will have a higher UV resistance property? You are absolutely true that for outdoor application you need higher UV resistance. Now my next question is to fix that my material should have higher UV resistance. What will be the properties or the structure I need in the backbone? So you know that UV resistance. Yes, yes. Yeah, yeah, yeah. Just tell me. No, 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 no. What you thought, you just you are not audible. Ah, yeah, I am listening. Yeah, you are audible. Uh, then I will ask you that whether you will. Okay, okay. So I am just ask you that. Then I will ask you that whether you are going to use natural rubber for outdoor application. May I use natural rubber for outdoor application because it has a very high molecular weight compared to any other rubber? Yes, because of higher mechanical property, you need NR. Now we know that maximum that is absorb the energy. That is true. That is mechanical stress. So that's why we use in our mainly in tire application. Yeah, yeah. Please repeat. Chemical property absorb energy means if you have a high molecular weight rubber, that means it has a very high chain length. Understand? Now next, if some polymer or rubber has a high chain length, if you provide mechanical stress, it can absorb by disentangling its chain. Understand or not? If I say understand, say for NR, because of it is high molecule chain length, it can absorb energy by entangling its chain. In that way, it can absorb energy. Now, the what I asked, that outdoor application we know maximum case EPDM is used, right? EPDM rubber is used for the outdoor application, like for in automotive sector, the all glass sealed or door sealed are EPDM based rubber. Why it is used? Why I am not using natural rubber? Because it has a high mechanical property, but still it is not used because it has a very poor weather resistance or UV resistance. Now, UV resistance depends on the chain structure. What is the main thing? That is the unsaturation. Whether unsaturation is present in the backbone of the chain, if unsaturation is there, obviously it cannot be used in the outdoor application, because in presence of UV, that unsaturation, that pi bond will dissociate and it will form two radical. When it will form the radical, ultimately the degradation will start. Clear or not? Okay. So if I have to choose some rubber, so I have first check whether there are unsaturation or not in the backbone. If there are unsaturation, I cannot use for the outdoor application. There may be some different requirement. The prime requirement must be it has to have UV resistance, and that will leads to saturated backbone. We need saturated backbone. In case of EPDM, there are no unsaturation in the backbone. If you see the structure, that is ethylene and polypropylene. After polymerization, there is no unsaturation in the backbone. That's why to cross-link the EPDM, we have to provide some uh, additive so that it can participate in the polymerization, and the cross-linking will start from the branches. It is not start from the your backbone. And also we need some different cross-linking agent. You may know that in case of EPDM, we maximum in maximum case we use some peroxide based cross-linking agent. It's not sulfur, because sulfur uh, required unsaturation to initiate the cross-linking. Okay. Now next is the physical properties. Physical properties means uh, your solubility, your optical property, or its toughness. Those are the physical properties. Now if the crystallinity is high, then what will be the impact on your solubility? Anybody please? If the crystallinity is high in your polymeric material, how it will impact your solubility properties of that particular material? Whether the solubility will increase or decrease? Solubility, yeah, solubility will decrease. Now why it will decrease? If I ask you why it will decrease, if the same material you prepared in some specific way, it has a higher crystallinity, and the same material you prepared, you change some process parameter and it has lower crystallinity. Now lower crystallinity will have a better solubility. Now why? What is the basic reason uh, before that? The crystallinity will leads to the lower solubility. That is true, more compactness. Now what I mean, that first thing, that for solubility it has to be the Gibbs free energy after making the solution will be negative if it is soluble in room temperature. Say for example NaCl. NaCl is crystalline, but it will soluble in room temperature in water. So the main thing is you need to know that if the change in Gibbs free energy before, I mean when you are making the solution, it can uh, predominate the crystalline energy or not. When it is forming crystalline material, so there must be some energy, because that's why it is crystalline. Now after making the solution, if the solution energy is higher than the crystalline energy, then it will undergo in the solution. That is the main fundamental concept. Because if you have excess money, then only you can go for a cinema. Yeah, please if someone is asking something. Yeah, it depends. Huh. More ordered from, yeah. Actually, see, the thing is, in case of polymer, the crystallinity concept, and in case of your inorganic oxide or different metal, the crystallinity concept is different. Understand or not? Because we have some unit cell structure, unit cells, different unit cell structure in case of inorganic material, but in case of polymer, the crystallinity concept is different. There are chain back and fold type of concept. It's not the unit lattice. Okay. Now the main fundamental concept is, when you are making a solution, if the after forming the solution, the Gibbs energy is uh, more than the crystalline energy, then it will disintegrate from the crystalline material and it will ultimately form the solution. For that, you need to know the solubility parameter, and that depends on the cohesive energy density. So if you, for the polymer, you may know the, for a specific solvent, if the solubility parameter are closing to each other, it is more soluble in that solvent. The same polymer, if it is soluble in polar, it may not be soluble in non-polar. The reason is that the cohesive energy density after forming the solution, whether it is increasing or not. Understand or not? If someone has doubt, please ask me. For example, your NBr, it may be partly soluble in your polar solvent, but it's not soluble in your hexane or cyclohexane. The reason is the solubility parameter is different. If you check the solubility parameter of your NBr and cyclohexane and NBr in some polar solvent, say dichloromethane, in case of DCM, it will be closer compared to your hexane. And when it is coming closer, that is much more soluble in that specific solvent. Okay. So if you don't know the solubility, first of all, if you know the solubility parameter, then you can clearly check that which solvent is preferable for the solution. For example, for a specific rubber, you know that solubility parameter is X, and if for a specific solvent, if the solubility parameter of that solvent is Y, and if a difference between X and Y is very low, so it has a higher tendency to be solubilized in that specific solvent. And the next thing is, we know that likes dissolve like. So non-polar rubber will be much more soluble in your non-polar solvent, and polar rubber will be much more soluble in your polar solvent. That is the basic thing. So for that, you first know the structure. For example, your fluoropyrin rubber. So there is a presence of fluorine atom. So that has a some polar property, polar nature. So it has a some tendency to be dissolved in your polar solvent. Okay. Okay. And also there is one thing, that if you cross-link a rubber, then you cannot solubilize in any solvent. It will be swelled, but it is not soluble. After cross-linking, you cannot do anything. It is set. Before cross-linking, it may be solubilized, but if once it is cross-linked, even if it is a polar, it will not be soluble in your polar solvent or any solvent. For example, if it is your natural rubber, if it is cross-linked, it cannot be soiled, it cannot be soluble in polar and non-polar solvent also. It will be soiled just. So here just I have given example that how the structure, monomer structure can change the property. This is the example of polyethylene and this is the polypropylene. So the crystallinity is different because of the very simple structure, only CH2 CH2 I have already discussed. Here is the presence of CH3, that's why also Tg is higher. Polypropylene Tg around minus 15 or something, but polyethylene is much lower. The reason is also the presence of bulkier group in CH3, and that will ultimately reduce the segmental motion. And also crystallinity is different. The next is the very classic example is the 1,4 polyisoprene. So if you know that what is the structure of natural rubber, someone please. Natural rubber has 1,4 polyisoprene. Now which one is the natural rubber? And then I will explain that how the structure can a great change in your ultimate final appearance and final properties of your material. It is a very simple structure, only CH3C double bond C, and the geometrical orientation is different, and because of that the material ultimately is absolutely different. So anybody, if you know, please, first one, that is yeah, that is true. This is the natural rubber. And what is this? This is the gatta parcha. Now you can correlate that how structure will affect in the property. It is rubber, purely rubber, but it's not rubber at all. And the reason is the crystallinity. Because of the C structure, it can very efficiently stack. It can interact very efficiently with another one. But because of this, the chain stacking is not that much efficient. In that way, it will impact your properties. Now, the another very important parameter is the transition temperature. So mainly there are two transition temperature. One is the glass transition temperature Tg, and another one is the melting temperature, that is Tm. Now what is Tg? Tg is the temperature below which the material is in glassy nature, and above that temperature it is flowable. So basically the temperature above which or at which transform to flow from glassy state to rubbery state, that is the glass transition temperature. Now what is the melting temperature? Melting temperature is at a particular temperature when the material is totally melted. But in case of polymer, we know it's not a purely crystalline, it is semi-crystalline. So we can say in case of polymeric material, that melting point or melting temperature is above the transform the segment chain mobility, and it will flow. That specific temperature is the melting temperature. Now the basic difference is the Tg is the second order transition, and your melting temperature is the first order transition. Now if I ask you that for a material to have Tg, what is the most important property to show the Tg? What is the chemical structure it should have so that it can show your Tg? Because any material, it's not possible to be have a specific TM or TG. Every material has TG and TM, but we know that for few materials they has very low TG, but there is a specific TM. But for polymeric material, it's always TG and TM. Now, what is the basic parameter or basic factor that actually control the TG or TM? Anyone, please? Presence of polar atoms, that is true, but that is a secondary one. I mean, I want to know the most basic one, and because of the presence of polarity, that basic one will change. So first I need to know what is the basic one, and then I can modify it by some incorporating polar group or different thing. My question is that if a polymeric material, we know that polymeric material has TG and TM, but we also know that for polymer the TM is not very sharp. If you check the DSC, you may see that TM is not very sharp in case of polymeric material. But if you use some inorganic material, you may get a very sharp point where the melting appears. But TG will be very poor in case of inorganic or small material. But in case of polymer, you may get a very sharp TG point in your DSC graph. Now, why it happens? Why in case of polymeric material TG is much more prominent compared to your TM? Uh, that is true, larger molecular weight, that is the prime factor. The main thing is TG and TM, that basically depends on whether the material is crystalline or amorphous. The crystalline material has TM and amorphous material has TG. Now, as we know that any material is not 100% crystalline or 100% amorphous, so that's why we get both TG and TM. But higher the amorphousness, we will get the much sharper glass transition temperature as compared to your melting temperature. But if the material is higher crystalline, the vice versa will happen. We will get a sharp point at TM for TM, but we will get very poor transition like glass transition. Now if you think that the amorphousness and crystallinity depends on your chain length, the higher molecular weight, it will leads to higher amorphousness. So that's why any elastomer, as I have already told, that molecular weight is in that range of 10 to the power 5 or 6, and so eventually it has a very higher chain length, and that's why every elastomer is amorphous. Now understand or not? Amorphousness is responsible for the TG and crystallinity is responsible for the TM. That is the main fundamental thing. Now what are the factors? That is cross-link density, branching, chain length, polar groups, aromatisms, etc. Those will affect your TG. For example, if you say that natural rubber without before cross-linking, it has a TG around -73. Now once it is cross-linked, so the TG will be higher. Now why TG is higher? Because we know the TG appears because of the segmental motion of your chain. Now you cross-link the polymeric chain, so you are resisting the segmental motion, so that will leads to your higher TG. The second thing is branching. So here you should clear it out that if you use higher cross-linking agent, so obviously there is a chance of higher cross-linking density, so higher will be the TG, so it will be rigid one ultimately. The next is the branching. The same thing, that higher will be the branching, your segmental mobility will be reduced. Because of that branching, it has a very the freedom of making the movement of segment will be difficult. The third one is the chain length. The same thing, that higher will be the chain length, the segmental mobility will be higher. Polar group. Now if there are presence of some polar group, so there must be some polar interaction or hydrogen bond interaction. So that will leads to the higher uh, increment of your Tg. For example, your uh, uh, say NBr, acrylonitrile butadiene, compared to your butadiene rubber, NBr has a higher Tg because of the presence of CN group also. Aromatically, polyethylene and polystyrene. Polyethylene is CH2CH2, and now in case of uh, polystyrene, there is a presence of one benzene ring. So because of the bulky benzene group, so it will hamper your segmental mobility, then Pg will be higher. So these are the I have given few uh, factors. There are maybe some other factors also, so that will control your Pg or Pm. Now if anybody has any doubt, please ask me. That is very important. Yeah, yeah. Okay. So first of all, we know that those handbag are mainly LDPE type material, and polypropylene we mainly use some bottle and also some table, etc., because it has bulkier CH3 group. Now the TG, in case of you have specified the application for packaging material. So if you think that TG has not that much importance in case of packaging application, the TG has importance whether in case of tire. In case of tire, the TG has a very important role. But in case of packaging, and even in case of conveyor belt, in case of I mean what I mean to say, from the TG you can assume or you can predict some properties, because if a polymer has a very low TG, that means, say for example, -70, and at room temperature, that means you may say that is right now 30 degrees centigrade. So the difference is 100 degree. Now higher the difference, an elastomer is much rigid in room temperature. I mean those polymer have very low Tg, so that means those specific polymer will be much more rigid in room temperature. Now in case of packaging, as we don't need that much of uh, mechanical property or abrasion resistance type of thing, so it's not Tg, it's not that much very important. But yes, one thing I have to highlight here, that if we are carrying some small weight, so maybe, or higher weight, so in case that it has to have some higher toughness. If it is carrying a higher weight material, heavy material, in that case you need some toughness. For that purpose, higher toughness also you can correlate Tg with the toughness. So previous slide, okay. Yes, please repeat. Actually, pure isoprene is naturally occurring material. Now natural rubber, it is cis form. Cis form means that is geometrical isomer. Cis and trans are geometrical isomer. So it is in the same direction. If you check that CH3 hydrogen in the same orientation, and the polymer chain is growing in that direction and in that direction. That's why it is cis. And the trans case, it is opposite. It is direction is opposite. That CH2 here and that CH2 is here. Now because of this, the packing is different when large chain is formed, and that will eventually leads to the higher molecular weight and also other different property, your uh, mechanical property. Cis and trans, these terms are applicable for the geometrical isomer. Okay. Now cis means in the same side, and trans means in opposite side. So if you check that the chain is growing in that direction, CH2 in that direction, because the radical is here and another radical is here, so it will grow in that direction and that direction. But in case of trans, you said that chain growing direction is totally different, opposite side. So that's why the packing after forming the large chain, so packing will be different in case of cis and trans. Now it is, this cis is not applicable for the polymer. This cis and trans concept is not applicable for the polymer. Here just to show you that the direction of growing chain is, case of cis it is in the same direction, but in case of trans it is in the opposite direction. Basically there is a geometrical isomer. Understand or not? Okay. So we have discussed, yes, 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 yeah, okay, yeah, absolutely, that is a nice question. So to tune the TG, sometimes you may not have that much sophisticated laboratory to, even it's not laboratory, maybe your synthesis from your monomer. If I change the monomer structure, then I can tune the TG. Now if I have no option to change the monomer, so it will be difficult, because again you have to synthesize a new monomer and finally it will be a different polymer and different property. Now how I can ultimately change the TG of the final product? So in that case we have to incorporate some plasticizer or additives. Now how it can change? Now plasticizers and additives, what they do, they penetrate in between the polymer chain. Now when they are in between polymer chain, so they are making the mobility is faster. They are reducing the chain stacking. In that way they are lowering the TG. So if you use some plasticizer or adhesive, it will lower the TG of your base material. Got it? Because actually what plasticizer do, plasticizers are very small molecule, they are not large molecule. So they interpenetrate in between polymer chain, and they will increase the mobility of two polymer chain. So first they have to diffuse, and then they will reduce the stacking, or they will reduce the interchain interaction. So okay, so polymers, I have not included here slides, because we know that polymers are different application, but then for some other high end application, polymer itself cannot be used. So then we have to go for the composite. So what is composite? Composite is basically composed of two different or more than two different constituents, and they have different role. The one constituent will provide some properties, another other constituents will provide some other properties. So the definition, you may say, it is made up of two or more constituents materials and provide superior property to the individual constituents. So here it is important to highlight that after forming the composite, the ultimate property of the composite material will be higher compared to your those beginning material. Now these has two phases, one is the matrix phase and another one is the dispersion phase. Now what is matrix phase? Matrix phase means it is the continuous one. It is a continuous material, and you are dispersing some additives or some fillers or something, some other material in that matrix. So matrix phase, it may be metal, it may be polymer, it may be ceramic. Now dispersion phase, so it is the structural constituents which ultimately determine the structural property of your composite. Now what dispersion material or additive material do? it will interconnect with each other and also with the matrix material, and it will lead to the higher mechanical property. For example, if you for example, tire, it's the best example of a composite. So there are lots of different components because itself rubber has not that much of higher mechanical property so that it can bear that much of load. So there is a continuous phase, that is rubbery material or elastomer, and to improve the mechanical property, what we do, we use usually carbon black, we use some steel cord or your fabric. So that is the second phase. Now the dispersion is very much important. If it is not dispersed properly or homogeneously, the property will vary. In different parts there will be a different property, it will be not homogeneous. And also it is important to choose the matrix phase. For that you need to know the viscosity of your material, how it can, because higher will be the viscosity, it will be different to disperse something in that matrix. For example, if you use NR and you are dispersing very uh, small particle size carbon black, it's become difficult because of the higher viscosity of your natural rubber and also the dispersion material. Here carbon black has a very small size, so higher surface area, so it will be difficult to disperse in the matrix. But if you properly or homogeneously mix, then overall ultimately the product will have a better mechanical property from your base material. And also it is important to know that additives or the second phase, those are in usually in small content compared to your matrix phase. It has to have a good interaction with your matrix phase, otherwise it will come out. After certain time it will be separated out from your matrix phase and your lifetime of your final product will be lower. If somebody has any question here, please ask me. Related to dispersion or composite, if anybody has any doubt, please ask me. Otherwise I will go to the next slide. Okay. So here I have set few question. So first one is, which one of the following technique give you idea about the percent of crystallinity of your polymer? So those are the four, there are four options: XRD, XPS, TGA, FTR. So we have discussed about the basic concept and application, classification of polymer. Now as the course name itself has the characterization of elastomer, polymers and composite, so we will discuss little bit about different characterization technique in this week, and later we will go in different other technique also. So we have discussed the crystallinity, we have discussed glass transition and other concept also. Now here I have set few question. So first one is the, which one of the following technique give you idea about percent of crystallinity of a polymer? Because from uh, anybody other else? Some another please, other one response please. uh, no, no, the right answer is the XRD. XRD is the X-ray diffraction. To know the crystallinity we need to perform the XRD. Now XRD will maybe later we'll discuss deeply about the basic principle of XRD and etc. But for this time being, this is the XRD, X-ray diffraction. From here we can get the crystallinity of your material. If somebody have already performed that XRD or have used XRD, usually for polymeric material we used to get a very broad peak, but as it is not purely crystalline material, but for inorganic or other crystalline material we used to get a very sharp peak in the XRD data, where we plot intensity versus 2 theta. So maybe in near future we will discuss thoroughly about XRD and other technique. So here, just for your interest, I am describing the full form. It is the X-ray diffraction, it is X-ray photoelectron spectroscopy. So maybe in 6th or 7th week we will discuss XPS. TJ is the uh, thermogrametric analysis, and this is for the thermal property, the thermal stability of your material. We need to do the TGA. So for crystallinity we need to do XRD. XPS is the for elemental analysis. We can say how much percentage of your some material is there by checking the different bond energy of your elements in presence in the material, and TJ is the therm to check the thermal stability of your polymeric material. TGA you have to do and FTR is the Fourier transform infrared spectroscopy. So why we need this? For to analyze the presence of different functional group in your polymeric material. So if you need to do the uh, reverse analysis, you have to perform all these testing to check what are the different elements or other properties. If somebody ask me few question about regarding this, I will be happy, or otherwise I will go for the second question. You have already seen it. Okay. The next question is the strain induced crystallization is observed in which rubber? Strain, okay, natural rubber, okay. Anybody else? Okay, yeah, that is true. You are absolutely right. That is natural rubber, and it is the only rubber that show these very interesting properties. Strain induced crystallization. So I little bit discuss about here what is the strain induced crystallization. Before that, these are the polystyrene. It is plastic, polyphenol acetate, polyphenol alcohol, and NR. Now, strain induced crystallization is you are inducing crystallinity in your material when you are giving the strain. Except NR, any rubber is not any rubber not show any strain induced crystallization property. That's why NR is so much important, and NR is so much vastly used in any rubber industry for high end application also. And you know that aero tire, those are mainly almost 100% NR based rubber. Now, why it happens? For strain induced crystallization, the chain length should be very much high. Now, as NR has a very high chain length, and we know that our mother nature can create things without any defect with most superior property. So it has a very high chain length. When you are giving strain, that means you are uh, stressing it, so chain are getting strengthened, and then it will more efficiently stacked with another chain. In that way, the crystallization is increased. That's why after certain time in your tensile stress strain curve for NR, the tensile strength or the stress is increased after certain elongation because of the crystallinity is increased. Okay. The next third question is the matching. So there are four uh, parameters: melting transition, glass transition, brittle failure, ductile flow. You are saying C. Okay, anyone else? Just C, D, another one is saying B. Okay, other one or anybody? Now, if who is saying D or B? Uh, okay, so B and D. Now, please explain who are saying it is D and who are saying it is B. If someone who is saying B, please explain why it is B, and those who are saying D, they are also first who have said B. Okay, B for Bombay. So you are saying B. Okay, okay. So first, just say that. So you are saying melting transition. B is the this one. So melting transition is crystalline. Glass transition is amorphous. Brittle failure is fiber, and ductile failure is elastomer. Okay. For those who have said D, please explain why you have said D. Then I will explain what is the right answer and why it is right. Because the option those are given, it may be applied some for two different options also. Okay, so the right answer is B. The right answer is B. Now I will explain why it is B. For example, the melting transition, it is true for crystalline and it is true for fiber also. Yes or no? Because melting transition is happened in case of fiber also. But when you compare that this is here, this is the most appropriate, that melting transition is crystalline. Among these four options, the most appropriate one is the B. Why? Because glass transition, obviously it will go for the amorphous, because amorphousness actually decides whether a material should have a glass transition or melting transition. So melting transition is crystalline, glass transition is amorphous. Now, among the brittle failure and ductile failure, you know what is ductile failure and brittle failure? Maybe in next there is another question there. I will explain what is brittle failure and ductile failure. So brittle failure basically that has a higher modulus, but it has a very low elongation. So this is fiber, and ductile failure is elastomer, because elastomer has a very high molecular weight and high chain length, but it has a very low tensile strength, but it can elongate more than 1000% also. So melting transition is crystalline, glass transition is amorphous, brittle failure is fiber, ductile failure is elastomer. So right answer is the B. If anyone has any doubt, please ask. Okay. Now next question is solubility increases with increasing temperature, increasing linear structure, increasing molecular weight, or all of the above. Okay, all the above. Anyone else? Okay, so till now A and D. Anybody else? Solubility, the right answer is A. Right answer is A. Now solubility increases with increasing temperature. Now why it is A? Because if you think increasing linear structure, that means you are increasing the amorphosity, crystallinity. So obviously the solubility will not increase. You are increasing the molecular weight, you are increasing different interaction, so it will reduce the solubility. What is the prime requirement solubility? That solvation energy must encompass all other interaction energy, then only it will be soluble. Now for that we know d del G equal to delta H minus T del S from the Gibbs energy equation. Delta G equal to delta H minus T delta S. Now if you increase the temperature, if you see the equation, the overall minus T delta S will be increased if you increase the temperature, keeping remaining all are constant, that is enthalpy and your entropy. So that will eventually lead to the higher negative delta G value. Higher the negative delta G, higher will be the solubility. This is very simple thing. So that's why with increasing temperature, your solubility will increase. That's why sometimes to prepare oversaturated solution, or sometimes for recrystallize some material for purification, we usually used to do that you solubilize some specific amount of a material in a specific volume of solvent. When you are increasing the amount of solute in solvent, when it is not soluble, just heat it at a 40, 50, 60 degree temperature, and then keep in a stable condition. When it is in room temperature, it will recrystallize, because you increase the solubility by providing heat. Now you are keeping it at room temperature, you are not providing any heat, so again it will recrystallize. Okay, so that's why with increasing temperature we can increase the solubility. For example, your sulfanylic acid, because of very high intermolecular deuterionic interaction, it is not soluble at room temperature in water, but if you provide heat, it will soluble in water. My slide is not moving. Based on tacticity, I have not discussed till tacticity. So tacticity, basically the orientation of your backbone repeating unit and different atope in that repeating unit. You have heard the term tacticity? If somebody responds, please. You have heard the term tacticity in case of polymer? Okay. Yeah, that is true. Absolutely right. These are three. Based on tacticity, we can categorize in three. So this is also one classification of polymer, that is atactic, symbiotic, and isotactic. And from here you can also determine the crystallinity. The isotactic and symbiotic have better crystallinity compare your atactic one. The reason is same. So if you know the basic, na, you can correlate with other parameter also, and you can you can predict the final properties also. So isotactic and symbiotic, because of the same chain orientation, the effective stacking will happen, and ultimately it will have a higher crystallinity. So based on tacticity, there are three: isotactic, symbiotic, atactic, and isotactic and symbiotic will have a greater crystallinity compared to your atactic one. And this is your standard stress strain curve. So here I will just a little bit discuss about toughness and hard, ductile, etc. So if you know that this term, so what will be the best option? Those are given here. Four options are given here. What is the most suitable one? Anybody, please. So first option is A is hard and tough. The B material, you just assume A, B, C, D, four different material, and we are uh, going to do the stress strain experiment, tensile strength experiment. So first one, it is hard and tough. B is hard and brittle. C is stiff and strong. D is soft and ductile. This is the option A. Now second option, Answer D. Okay, so three body responses. Anyone else? Okay, the right answer is D. Now please explain why D is the right one. Those who have choose the option D, please explain why you have chosen it. From the graph, from the, yes, from the stress strain graph, just explain. Yeah, yeah, that is true. You are absolutely right. Good. Because it has very low strain, but it has very high modulus. Now, higher will be the modulus, it is much more hard and brittle. So it is the much more, the slope is very high in case of A compared to B, C, D, and we know the stress by strain is the modulus. So in case of A, the modulus is very high, and obviously it is very hard. But as after maybe it is 2%, 3%, it is broken apart, so it is brittle enough. So it is hard and brittle. Now the B is stiff and strong. Why it is stiff and strong? Now compared to A, it is not that much stiff, because stiffness is more related to your modulus. But why it is strong? Because after some point you say there is a bending is happening here. That means it can take some strain. You can stretch it maybe up to 20%. That's why it is strong. Now C is hard and tough. Now actually hardness is related to your modulus. Hardness, stiffness are related to modulus. Now what is toughness? Toughness is the total area under the stress strain curve. For any material, the area under the stress strain curve is the toughness. Sorry, yeah, exactly. It is the ability to absorb energy. So higher will be the area, higher will it will the absorb energy. But as the slope is not that much high as compared to your AB, so uh, it is less harder than AB, but it is harder than D. But after some strain, you see there is a very slowly increment of your stress. That means it can absorb that much of energy. That's why it is tough. The next one is the D, that is very soft. The Young modulus is very low, but after a certain point, you see there is a increment of your stress strain curve. So that's why it is the ductility behavior from the stress strain curve. You may say if some material has this kind of nature, that slowly it is increasing, and after a certain point it is increasing in that way, it has the ductile nature. So usually rubber has a ductile nature. Okay, so thank you for your patience and your interaction. If you have any doubts, you may. Thank you for your kind words, and I am also learning from you because I'm not that much of expert in that field, but still I am learning also. And thank you for your interaction. So maybe my English is not that much fluent, so you have to tolerate with me for upcoming few days. And it is great for me also. I'm interacting with different people. Yes, yes. Thank you very much. I am also clearing my doubts. If I have doubts, you may ask question. Maybe in next week, maybe after few days, I may give answer. But you should ask me question so that I can also gather knowledge from you also. Thank you. Thank you. So I am leaving for today. Again we will meet in next Saturday. Till that, keep well and be healthy, happy, take your time, enjoy. Okay.